Good morning, everybody, again. My name is Mina Khoshrangbaf. I'm a PhD student at Ege University in International Computer Institute, and today I would like to present about clone-based coverage optimization in wireless sensor networks. But first, I would like to tell you why we need such a method. In recent years, the new generation of smart buildings, vehicles, and factories are widely dependent on the proper sensing and collecting data from environment. Wireless sensor networks are one of the technologies that can be used to collect different kind of information from various environments. But the problem is that sensors should cover the maximum possible area and be in communication with each other at the same time. This is a confliction because one leads the sensors to be far from each other and the other one needs a dense network. So as a solution, researchers propose to use a predefined deploying pattern, but this is not applicable for all environments, and there have some problems. Due to good performance of evolutionary algorithms in various fields, they are used to find the best deployment points for nodes in this area. Algorithms like a genetic algorithm, particle swarm optimization, and ACO. Researchers consider assorted conditions for investigating, like taking the communication into account or not. Particularly for ACO, proposed methods that use ACO focus on finding minimum possible number of sensors to cover an area, or to increase the costs, or to cover predetermined critical points in area. But what is clone optimization that we use in our approach? It means you have noticed that the most ants use the same path to go from a point to another. They can find and inform other ants about the best road thanks to pheromone that they leave on their way. And cloning optimization algorithm use the same strategy. Algorithm starts with a set of random solutions, update the pheromone matrix, and improve them until satisfying a predefined subcondition. For our proposed method, as first step, we model the solution space as a graph for ants to travel on it and create solutions. In this graph, N is the number of sensors that need to be deployed on the area, and M is the size of one dimension of the area, which we supposed to be square in this problem. Every ant, by traveling on this graph from start to end, generate a path that symbolizes the deploy coordinations for N sensors. For example, as a sample, you can see the coordinations for 8 sensors. The first cell is the coordination for the first cell. It means it could be, it should be on for 25 and 80. And at the next step, we need to evaluate these solutions. We use the reverse of coverage rate as object function, but moreover, we add a penalty to it. Coverage rate is the ratio of the area that can be sensed by sensors to the whole area, and penalty is the function of the number of sensors that are not in the communication range of any other sensors that we don't want to be happen, and this is a hard constraint for us. And after that, we can say that our whole approach works this way. The deployment plan is generated by an ant and is evaluated using the object function that we saw now. Then the Fermat matrix is updated based on the quality of the solution. At the end, the stop condition is checked. The approach stops if the condition is satisfied, and if it is not satisfied, the loop will be repeated. For such evolutionary algorithm, we need to set some parameters beforehand. For this and to find the optimal values for our algorithm's parameters, we have implemented the approach with different values and chose the best ones based on the result. The optimal parameters are shown in this table, which includes the number of iterations that we take it as the stop condition, the population size, the number of ants that we need to start the algorithm. Evaporation rate is a parameter for updating Fermat matrix, and penalty coefficient that we use in our objective function. So for evaluating of our proposed approach, we implemented it on MATLAB, using MATLAB. The first diagram that you can see show that how coverage rate increase as the algorithm iterates. This is the diagram for one sample with, as you see, 32 sensors and 10 meters sensing range for the sensors. That you can see that it increases by as the iterates go forward. And in the second diagram, we, in order to compare and evaluate the impact of the numbers of sensors and sensing range on the coverage rate, we executed the algorithm for 3 different sensing radius. You can see them in 3 colors, 5, 10, and 15. And also for 18 different number of sensors from 20 to 600. It seems that sensing radius is more effective and give high coverage rate with just 40 sensors. So this is useful for us. So we can decide on the sensing radius and number of sensors for our problem based on the area condition, available sensors, and using this diagram. To see what our method does more clearly, we visualize the situation of the sensors before and after optimization. You can see that the difference between covered area of the random deployment, on the left side, and optimized deployment on the right. These are two visualized diagram for 2 samples. The first row is for 14 sensors with 15 meters sensing radius, and the second row shows the result for 32 sensors with 10 meters radius. You can see that the area covered after optimization is much than the before optimization, and the sensors can cover more area. But we aim to propose a method for deploying sensors such that cover the maximum possible area to be in and be in communication with each other. The results show that our ACO-based method can improve the coordination of the sensors in the order to achieve our goal. The evaluation results shows that this method have good performance for problems with different number of sensors and various sensing range. And so we can use this method to increase coverage rate and optimize them for a set of sensors for any problem. And this leads us to a better result of data collection and also decrease our cost. Finally, as the future work, we left the verification of the result in reality for our next study. Finally, I thank the organization and my advisor for this opportunity, and thank you for attention.
Thank you very much, Mina, for the presentation. I start the question session. So, Andrew, please ask the question.
Hello. I have one question. Whether the proposed method can be used only for the network with fixed sensor nodes or also for the networks with high node mobility? Maybe you try to compare these two types of networks.
This is for now just for the sensors that are not mobile, because we just find the coordinations for deploy them. But this can be used as the first position for mobile networks, and they will have good result in the next processes.
So I can hear Marek. So I'd like to ask you, the critical parameter of each node is source of the power. Did you consider this problem if in your model? Because I ask because this I am not sure that all batteries of the nodes will be work in the same time. What will be the problem when one of the sensor was died because of the power?
Yes. We didn't take it into account directly, but this algorithm help it indirectly. When we deploy the sensors in most better, good places, good coordinations, they can collect data efficiently, and maybe the time needed for collecting data decrease. So this can help to, in case of lifetime of sensors.
Okay, thank you.
Thank you too.
Okay, Jarosław, please ask the question.
Hello, can you please indicate the best application of such ant colony optimization? I mean, it's not good for military ad hoc networks, isn't it?
Can you repeat? Sorry, I didn't understand.
Could you indicate the best application of such ant colony optimization? Practical application.
Yes, I didn't compare. We didn't compare the ACO algorithms in this area with each other, because they consider different, assumptions and conditions. Some take just focus on lifetime, just some focus on covering critical points. And there is now ACO-based method that try to cover the whole area and taking into account the communication. So we didn't do a comparison.
Okay, thank you.
Okay, is there any more question? If not, I have the last one question about the stop conditioning of algorithms, because you have how you evaluate this value 200.
You mean the area size?
Not really. You have the number of iterations set to 200, and this is the stop condition of your algorithm, as far as I understand. How you find this value 200?
In such evolutionary algorithms, generally when iteration, after a point, increasing iteration doesn't affect. so on the objective function, well, it is not logically to increase it that much. As our implementations, we find out that, well, after 200, it does not were so effective. So we, because of the, I mean, in view of the time, we decided on this.
Okay, so you have, this is the result of the experiment with this algorithms which you prepare.
Yeah, yes. Yes,
Okay.
the parameter all are set by experimenting various problems and decided on it.
Okay, thank you very much. I don't see more question. Thank you very much for interesting discussion and the presentation.